Swayam Prabha. Digital India. Educated India.
Let me continue. There is one point I wanted to reiterate, make explicit during this proof. Okay, so I just highlight that. So you see, in this in the proof of the surjectivity, namely, we have this situation where you are given a so the situation is like this. See, you are given you see a function capital phi s, okay, and another function capital psi s, okay, and this capital phi is should be you are trying to find a curve, space curve, for which this capital phi is the curvature function and this capital psi is the torsion function. Okay, so suppose you are given these two functions, capital phi s and capital psi s, okay, and you want to find a curve for which these two functions are respectively the curvature and torsion functions. If there is such a curve, then the curve should have a Frenet-Serret frame which is given by Fs, Gs, Hs, and it should satisfy this Frenet-Serret differential equation. Okay, so you first take a solution of this differential equation, okay, and then the important thing that you do is that, because if you want, because you would like to have a particular curve, so you need a particular solution, so you put some initial conditions. So the initial condition is that at some point S0 you make the Frenet-Serret frame to be a known fixed frame. So for some S equal to S0, we have taken the frame to be the standard frame I cap, J cap, K cap. Okay, then there is a solution. Okay, what is not clear is that this solution is at every S, it is a right-handed orthonormal frame that we had to prove. So essentially this meant proving that that this Fg and H, if you take the dot products, okay, which amounts to taking the FGH as a matrix, okay, mind you, F, G and H are treated as column vectors, and this is a 3 by 3 matrix, and you take its transpose and you multiply, you are trying to show that this is identity, and this is the same as saying that the matrix is orthogonal. Okay, and then you have to show also determinant is 1 to prove that it is right-handed. So therefore you are reduced to proving that these 9 dot products, because it's a symmetric matrix, there are only 6 involved. You have to show that these dot products are respectively 0 or 1, in the sense that F, G and H should be mutually orthonormal. Okay, they must be mutually orthogonal, they should have length 1. All right, now for that what you do is that you take these 6 relations, namely the self dot products are all 1 and the mixed dot products are all 0. Okay, and you are trying to show that this always holds. What is known is it holds only at S0. At S0 it is Ijk, therefore these conditions hold, but you want to show that it holds for every S. And what we did was we interpreted this as so you see, if you want all these 6 dot products to be constants, the derivatives of these dot products, you have to show that they are all 0. Okay, and that we interpreted it as a differential equation like this. Okay, so you had this differential equation where you had the derivatives of the 6 dot products, okay, is equal to you get a matrix times those 6 dot products. Okay, and why you are getting this matrix is because of the fact that because of the fact that these F, G and H, they satisfy the differential equation. Okay, so the derivatives of these 6 dot products are again linear in the 6 dot products. So you get a system of 6 homogeneous first order linear simultaneous differential equations, and you want to check that this system, of course by uniqueness of solutions, if this system has two solutions which have the same initial condition, then they have to be always the same. So what we noticed is that for these 6 dot products, if I put these 6 constant functions, namely that just corresponds to the choice that all the self dot products f dot f, g dot g, h dot h, they are all 1, okay, and the remaining mixed dot products they are all 0. If you put these constant function values, then you have to check that also satisfies this differential equation, okay, and there checking has to be done. The exact nature of the entries in this differential equation is important, okay, and for example if you take d by ds of f dot f, this turned out to be 2 phi s f dot g, and if you put f dot g is 0, okay, then you will get that this is 0, okay, and similarly if you calculate d so the moral of the story is what I want to say is that basically what is the claim that this satisfies the differential equation? The claim is that if you plug this constant on the left side, you will get 0 everywhere here, okay, whereas there is this matrix here, and if you put this on the right side, this is a non-zero column, mind you, okay, it is 1 0 0 1 0 0 1 0 1, it's not the 0 matrix. And what the important thing is, you have to show that this matrix will kill that and give you 0 0 0 0 everywhere. That means you have to show that all the derivatives are all 0, and I am saying that is because of this thing. If you put f dot g equal to the constant 0, okay, instead of f dot g you put the constant function 0, then this calculation will tell you that d by ds of f dot f is 0. Similarly, if we calculate d by ds of f dot g, okay, you use the Frenet-Serret relations, okay, the differential equation satisfied by that, you get this expression. Again, in this expression, you see, if I put g dot g equal to 1 and if I put f dot f equal to 1, then these two terms will cancel. And if I put f dot h mixed dot product is 0, that will also go away. So I will get that this is 0. So like this, you have to write down all the cases and check that if you put f dot f, g dot g, h dot h equal to, if you replace it by 1 1 1 and all the mixed dot products by 0, then all the derivatives vanish. That is the verification that these 6 constant functions satisfy the differential equation. And then the argument is that the solution that you have taken f g h, if you take the corresponding dot products, that actually equals this at that special point s equal to s naught, because there it is actually ijk. F g h are exactly ijk. Therefore, two solutions, a constant solution and a solution that you have in mind, they are equal at one point. Therefore, they are equal. That means actually these f dot, all these dot products are actually constants, and they are and what are the constant values? They are the constant values at that point. So I just want to point out that in order to use the theory of uniqueness of solutions of differential equations, you need that there is some matrix here, which is which consists of scalar functions. But really the form of the matrix is not important, okay. But to check that this is a solution, that this constant vector 1 0 0 1 0 1 is a solution of that, you need to calculate the terms of that matrix, and you have to show that the left side evaluates to the 0 column, okay. So that is a point that I did not explicitly state, okay, but one needs to check that, and it's quite straightforward, okay. So this is something that I just reiterated just in case it has been missed, all right. Now what I want to say is that this classification theorem, this is the classification theorem for space curves, okay. There is a similar classification theorem for plane curves, and though a plane curve is also a space curve, if you think of the plane as the xy plane sitting in 3 space, You cannot get the classification theorem for plane curves from the classification theorem for space curves, and we have to do that separately, okay. And the plane curve case is different from the space curve case is because of two things. Of course, in the plane curve the torsion is 0, okay. The other thing is, instead of the curvature you have to use the sine curvature, okay. Therefore, I just wanted to say that, you know, we need to look at that. So we need to do this classification theorem for plane curves. And why this is important is because in this case the signed curvature and the signed normal will play an important role, okay. The curvature will be signed, that is one thing. Then the other thing is that you are also going to use this idea of turning angle, okay. If you go back and think about it, you see, even in the plane curve case, the Frenet-Serret relations came only from the they came from the idea of the turning angle. Basically, the sine curvature was interpreted as the derivative of the turning angle, and we also use the result that every C1 unit vector, okay, on the plane is it possesses a turning angle, okay. So the turning angle is a very important starting point for all this, okay. So we need to use that. So I want to say, so first thing I want to say is that, so here is a fact. So the fact is, you can't get the classification theorem for plane curves using that of space curves. Okay, so see, what we need to do is we need to have a proof of the classification theorem for plane curves, okay. And the statement is that a plane curve is completely determined by its sine curvature, but up to a rigid motion, okay. So this is analogous to the the theorem, classification theorem that we have for space curves, which says that a space curve is completely determined by its curvature and torsion functions, okay. So what does that mean? If you give me a a non-zero curvature function and a torsion function, okay, you can find a plane, you can find a space curve which has these as the curvature and torsion functions, and any two such curves with the same curvature and torsion function will differ by a rigid motion. That is something that we have already done, okay. But we want to do a similar statement for plane curves. So you want to say that for the plane curves the determining factor is the signed curvature, okay. So the difference between plane curves and space curves is that in the plane curve case there is no torsion, but there is signed curvature. In the space curve case you have both curvature and torsion, but the curvature is taken as positive, if you want, all right. So we take only the magnitude of the curvature. The sign is controlled by the torsion, okay. And the sign among two quantities, curvature and torsion, the sign of the torsion is enough to control the handedness, okay, in the space curve case. But in the plane curve case, just the unsigned curvature is not enough, okay. You need the sign of the curvature because that is what will control the orientation, okay. And the simplest thing that you can think of is you can take a circle with the same circle with two opposite orientations, anti-clockwise and clockwise orientations. They will have the same magnitude of curvature, okay, but one will have negative curvature, sine curvature, and the other will have positive sine curvature, and you cannot move one to the other by a rigid motion, okay. See, you can superimpose one on the other by a rigid motion, okay. If two circles have the same radius, I can literally translate the center of one to the center of the other, and I will be able to superimpose the one circle on the other that way. But it's not just enough to superimpose. What is important is that even after you superimpose the senses of rotation, the way you traverse a circle, that also has to match. So if the two circles had opposite orientation. Okay, one was traversed in the clockwise sense, the other was traversed in the anti-clockwise sense. Then what will happen is that by a rigid motion I can superimpose one circle on the other, but even after superimposition you will see that these two circles, the way they are traversed, it's the same circle, okay, but in one of them it is traversed in the clockwise sense, in the other one it is traversed in the anti-clockwise sense, okay. So that does not match. The only way you can match that is you will have to go into 3 space and you have to rotate the circle by a diameter, okay, about a diameter as axis. Then you can do this, and this rotation in 3-dimensional space is a rigid motion, okay. But if you don't go to 3-dimensional space and stick to only 2-dimensional space, you will have to use a reflection across a diameter, and the problem is that a reflection across a diameter in 2-dimensional space is not an oriented isometry, okay. So it's not possible to move an anti-clockwise circle by rigid motion to a clockwise circle of the same radius, okay. And therefore these two are distinct, and how are they distinguished? They are distinguished by their signed curvatures, okay. So we want to make a statement like this, so let me write this down. Classification theorem for plane curves. So what you are going to do is that on one side, so you are going to take going to start with the curve gamma of s, unit speed curve, by increasing arc length s. S is varying in this open interval AB inside the real line, okay, and so it need not be the whole of the real line, or it could be, really doesn't matter, right. So I'll just put it like this, and of course this I want to talk about curvature and of this curve. So gamma should be in C2AB, so it should be twice continuously differentiable, all right. And then what happens is that for gamma I can define the sign curvature Ks sub gamma, okay. And how is this case, how is the sign curvature defined? So so this is a the sign curvature is defined by looking at the sign normal, okay. And if you recall, so the situation is like this. So you have the real line, you have this interval AB, and this is my S, okay, and then I have this map gamma, okay. By the way, remember that gamma is unit speed parameterized. What it means is that norm gamma dot is actually 1, okay. So which is of course d gamma s by ds, okay. Norm of that is 1, so it's unit speed parameterized, okay. And mind you, d gamma s by ds is a velocity, norm of that is the speed, and that has to be 1, right. And of course we are only working with regular curves, okay. Curvature is defined only for regular curves, and regular curves can be unit speed parameterized, okay. And then the curvature of a regular curve is defined as the the magnitude of the acceleration vector, okay, of a unit speed parameterization. And the unit speed parameterization is going to be essentially unique. It will always be plus or minus the arc length function plus a constant, okay. And so it's essentially unique. So we are using increasing arc length, okay. And so you have this picture where you have this gamma here, and if you give me a point S0, I am going to get this point gamma of S0, okay. And you see, at that point I will have the Frenet-Serret frame. So I will have this t cap gamma at S0. This is the tangent vector, this is unit tangent vector, and what is this? This is just gamma dot of S0. That's what it is, okay. Then you have the so-called sign normal. So the sign normal is in this direction. You are going to have this is n. So the subscript is capital S for sign, and the small s is for arc length. Don't get confused. So you have ns cap at S0. This is the sign normal, and the way you get the sine normal is taking the unit tangent and rotating it anti-clockwise by 90 degrees. Okay, so that is how the sine normal is defined. Then the point is that the curve, what could happen is that the sine normal may point towards the center of curvature at that point, or it may point away from the center of curvature at that point. If it points towards the center of curvature, then the sine curvature is positive. If it points away from the center of curvature, then the sine curvature is negative. That's how the sine curvature is defined. Okay, and you have this, you have the Frenet-Serret relations, namely T cap gamma, ns cap gamma, d by ds of that is equal to the Frenet-Serret matrix. It's going to be 0, k gamma, ks gamma, okay, and minus ks gamma 0, and on this side you will get again T cap gamma, ens cap sub gamma. So okay, so these are the Frenet-Serret relations, all right. And so basically what you do is that for every curve you give the you associate the sine curvature. Okay, and the point is, where does the sine curvature lie? It lies, mind you, the sine curvature is essentially second, based on the second derivative, so it will be continuous. Okay, and it is we always follow this rule that whenever you are looking at a derivative, you assume it's continuous. So the point is that this ks sub gamma will be actually in C0ab, so it will be a continuous function. Okay, so this way what happens is that we are able to define a map like this. So you have the set of all unit speed gamma of s, unit speed gamma in C2ab, okay, and you have curves like this, okay, and on the other side you have C0ab, okay, and so this is my map. You give me any such gamma here, okay, and you send it to the sine curvature of gamma, okay, and so what is the statement? The statement is that on the left side, if you go modulo the rigid motions of the plane, okay, that will be an equivalence relation. On the left side you will get equivalence classes of plane rigid motions of curves. Okay, on the right side and on the right side, of course, you have continuous functions on AB. Okay, C0 is just continuous functions. Okay, then there is a one-to-one correspondence, and this is the this is the mathematically precise way of saying that a plane curve is completely controlled by its sine curvature. Okay, so there are several statements we have to prove if we go modulo the equivalence given by rigid motions of R2. This is very, very important on the LHS. The claim is that the above map induces a bijection that is a one-to-one correspondence. Okay, so basically what is it that you have to prove? So what does this entail one to prove? So we have to show suppose gamma 1 is equivalent to gamma 2 under rigid motion, M a rigid motion. Okay, yeah, so what does it mean to say that you are going modulo the equivalence relation? That means you take a set, taking a set and going modulo an equivalence relation means that you are looking at the equivalence classes of that set. Okay, that means you are you are partitioning the set into disjoint equivalence classes, and you are treating each equivalence class as a single point. Okay, so that means you are treating all curves which are equivalent to each other by rigid motions as a single curve. Okay, as the so this is the idea that you this is the idea in mathematics that you have a set consisting of different types of different varieties of mathematical objects, but they are all the same class of objects. Okay, then you want to classify them up to some kind of isomorphism or some kind of equivalence. Then what you do is you try to put all the things that are equivalent to one another into a subset. Okay, and in this way you do it for every element. What happens is that you chop the set into these equivalence classes, and then and if you look at the number of equivalence classes that you get will give you the number of such objects, and different in the sense that objects that are not equivalent or not isomorphic. Okay, so isomorphism is a very special case of equivalence, but equivalence is more general. Okay, so you see that's what you're doing. On the left side you have to go modulo the equivalence relation. Okay, that means you have to take equivalence classes. Okay, and this is exactly the same kind of thing that we do when we take space curves. Okay, only there in the case of space curves we use rigid motions of R3 because these are in space. But here we are restricting to plane curves, so you should use only rigid motions of R2. Okay, so what are the things you have to show? You have to show that if two curves are equivalent by a rigid motion, what does that mean? That means gamma 2 is m circle gamma 1. That's what it means. You apply gamma 1, you take gamma 1 and you apply m to it. Okay, then you should get gamma 2. So this should imply that if you take a curve and move it by rigid motion, you have to show that the original curve and the new curve, they have the same sign curvature. Okay, this implies that k signed gamma 1 is equal to k signed gamma 2, which is the same as k signed em circle gamma 1. So basically k signed gamma 1 is the same as k signed m circle gamma 1. That's what you have to prove for whenever m is a rigid motion. And let me insist, I will put it here, of R2 is very, very important. Okay, so this is so you have to show this. Okay, once you show this, what happens is that it will tell you that from on the left side, if you take equivalence classes, then this map is well defined. Okay, okay, so I think yeah, so if you take two curves that are equivalent to one another, on the right side the associated sign curvatures are the same. That means this map of taking a curve and associating it to its sign curvature, that really does not depend on the curve. It depends only on the rigid motion equivalence class of the curve. Therefore, that map is defined on the rigid motion equivalence class itself. So this first condition is the necessary condition. Okay, that this map is defined even on equivalence classes. For a map on a set into another set to go down to a map on equivalence classes, it has to be constant on the equivalence classes. That means its value on the equivalence class should not depend on which representative you take in the equivalence class. Okay, so that is the first statement. Then so that gives you the map. Then you have to show that that map is both injective and surjective. What is the injectivity? If you take two equivalence classes, and if they are represented by two curves, if they have the same sign curvature, you have to show that this is one and these two equivalence classes are one and the same, which means that you have to show that there is a rigid motion that moves one to the other. Okay, so that is the injectivity. Okay, so let me write that down. If gamma 1 and gamma 2 have the same sign curvature, okay, ks gamma 1 is equal to ks of gamma 2. Okay, then there exists a rigid motion m such that gamma 2 is M circle gamma 1. Okay. If two curves have the same sign curvature, then one can be moved to the other by a rigid motion. Okay. What does this mean? This essentially means that if one can be moved by a rigid motion to one another into the other, it means that they are in the same equivalence class. Okay. So that is you see the equivalence class, rigid motion equivalence class of gamma 1 is equal to the rigid motion equivalence class of gamma 2, where this is equal to the rigid motion equivalence class of gamma. Okay. So basically what you are saying is that you see to gamma 1 you are associating this sign curvature k as gamma 1. To gamma 2 you are associating k as gamma 2. Okay. And gamma 1 is representative for box gamma 1, square bracket gamma 1, which is its equivalence class. Gamma 2 is representative for the equivalence class square bracket gamma 2, and these two equivalence classes are being associated to the two curvature functions which are the same. Then you are saying these two classes are one and the same. That means you are saying that this map from equivalence classes is actually injective. So this is the injectivity of the map. So let me also write that side by side. So that what it means. So this one is the map square bracket gamma going to ks sub gamma is well defined on rigid motion equivalence classes square bracket gamma. Okay. So you get the first statement is that this map is well defined on rigid motion equivalence classes. The second one is that the map is actually injective. Okay. So what does this mean? This means that the map square bracket gamma going to ks sub gamma is injective. Okay. So if ks gamma 1 is equal to ks gamma 2, then square bracket gamma 1 is equal to square bracket gamma 2. That's injectivity. Then you need to prove surjectivity, which is the next statement. So the third one, suppose phi of s is it's a continuous function on AB. Okay. Then you want to show that there is a curve, unit speed parameterized curve, for which this phi is the sign curvature function. Okay. Then there exists gamma unit speed parameterized such that k sub s gamma is actually phi. Okay. So so what does this mean? This is another way of saying that this map is actually surjective. So the map capital gamma to ks gamma is surjective. Okay. Surjective onto C0AB. Okay. So therefore these three statements will give you a bijection between the equivalence classes of rigid motion equivalence classes of plane curves and sign curvatures. Okay. And that is a classification theorem. All right. So let us look at the proof of this. So what I want to say is that, again, let me insist that you cannot get this classification theorem for plane curves from the classification theorem for space curves. Okay. Because to begin with, in the space curve case, you are not using sign on the curvature. Okay. And the sign is taken care of by the torsion. All right. Whereas in the plane curve case, you have to use the sign curvature. So you see, therefore the proof in the plane curve case has got to use essentially and the idea of sign curvature and what is special about the sign curvature. So what is special about the sign curvature of a plane curve? If you go back and think about it, the sign curvature is actually, the sign curvature was introduced geometrically. The sign curvature was introduced geometrically because you had this situation that, the normal was, ambiguous. Okay. Remember, when you give me a curve at every point, the tangent is not ambiguous. Okay. But the normal direction is ambiguous. Even in the plane, you only have a normal line, and you have two possible directions on the normal line that you can choose, but which one will you choose? So that is in order to resolve this once and for all, what we do is we choose what is called the sign normal. You take the tangent, which is well defined, and then rotate it counterclockwise by 90 degrees and call that the sign normal. Okay. So, but once you introduce the sign normal, the problem is that the sign normal may point towards the center of curvature, or it may point away from the center of curvature. Okay. Therefore, what you do is that you put a sign on the curvature to adjust this. Okay, that's how you get the first Frenet-Serret relation. Okay, so you get this sign. So you see, the sign on the curvature is only put to make sure to adjust the two cases when the sign normal is pointing or not pointing towards the center of curvature. When the sign normal is pointing towards the center of the curvature, the sign curvature is positive, and when it is pointing away from the center of curvature, the sign normal is negative. Okay, but this is only a geometric, seemingly ad hoc kind of definition. But why is it analytically correct? So we saw that, the reason why this is analytically correct is because the sign curvature is actually the derivative of a turning angle. So that was the technical thing. The technical thing is that the sign curvature, which came out geometrically as an ad hoc adjustment, it is also analytically well defined. It is so. What happens is that if you have a unit vector which is C1, then that vector can be written as cos theta sin theta, where the theta is the turning angle. It is the angle made by the vector with a fixed direction, which we usually take it to be the positive x-axis if you want. Okay. So since every C1 unit vector admits a turning angle, if you take a unit speed parametrized curve, its which is C2, then its unit tangent will be C1. So the unit tangent can be written as cos theta sin theta, and it turns out that the derivative of that theta with respect to s is exactly the sign curvature. So the sign curvature is the derivative of the turning angle, and this is analytically well defined. Okay, so you get an analytic description of something that we have defined ad hoc in a geometric way. And so, our definition is also therefore not really dependent on geometry. There is an analytic basis to it. Okay. So, therefore, what I am trying to say is that in order to prove all these statements, which are only in the plane curve case, you have to include the sign curvature, and the sign curvature is connected with the turning angle. Therefore, all these statements, the way to approach the proofs is that you have to think about the turning angle. Okay. The turning angle is the key to proving all these statements. All right, and I want you to remember that the turning angle itself was the the starting point for defining the Frenet-Serret relations for a plane curve, and it's only because of this turning angle interpretation of curvature of sign curvature that the sign curvature is derivative of the turning angle. That is what gave you results such as if the sign curvature is 0, okay, then the curve it will essentially mean that the turning angle is constant. Okay, and then you get the statement that if the curvature is 0, the sign curvature is 0, okay, then the curve is part of a straight line. Okay, then you also get this other nice statement that if you for a closed smooth curve, if you and actually the closed smooth curve can have also intersections, it really doesn't matter so long as it's smooth. Okay, then if you take the tangent vector and go around once, then you see the total curvature, okay, will be an integer multiple of 2 pi. That fact also comes because from this, because you see, when you take total curvature, you are integrating the you are integrating the curvature at every point, but the curvature is derivative of the turning angle, so you are integrating the derivative of the turning angle, okay. But then that amounts to simply finding the difference in turning angle at a starting point and when you come back to that point, which is the ending point, because it's a closed curve, okay. And then it's clear that this angle must be integer multiple of 2 pi, okay. So why is the total curvature an angle, and why is that angle an integer multiple of 2 pi for a closed curve? That is because of the fact that the curvature is actually derivative of a turning angle, okay. And there is a very special case which is called the Hopf-Umlauf-Satz, which says that if you take a simple closed curve, okay, then the turning angle the turning angle will change only by plus or minus 360 degrees. So that means the total curvature for a simple closed curve will be only plus or minus 2 pi, okay. And this is called as Hopf's Umlauf-Satz. It's Hopf's rotation theorem. So you see this, I am trying to impress that everything is for plane curves is based on the turning angle, okay. And that is essentially, that needs to be used in the proof here, okay. So so let us try to prove these statements one after the other, so I think the first one, so in order to proceed, you need to know how rigid motions in R2 look like, okay. So so you see, the first statement that we are trying to prove is that if two curves are rigid motion equivalent, then you want to show that their the sign curvatures are the same, okay. So you must understand what are the rigid motions of R2, okay. And then the fact is that any rigid motion of R2 can be written as it can be broken down into a translation, okay, and a harnessed rotation about the origin, okay. So this is similar to the rigid motions of R3 case, that any rigid motion R3 can be again broken into a translation into and another map which is going to be a linear isometry, and that will be a oriented linear isometry. And I told you that it will be a member of the a special orthogonal group in 3 dimensions, okay, and that is a generalized rotation, okay. So in 3 dimensions, what you can have is that you can have a rotation about an axis, okay. And in 2 dimensions, what you can have is just a plane rotation. That is the only possibility, all right. And this needs to be understood. So the claim is that in 2 dimensions, you take any rigid motion, which is by definition an oriented isometry, you can break it down into a translation and a rotation, okay. And this translation and this rotation are unique, all right. So we need the following fact: if M from R2 to R2 is a rigid motion, that is an oriented isometry, okay. And some books and some authors use the word direct isometry, okay. For example, Presley uses the word direct isometry. So direct means oriented, okay. Then you can write M is equal to translation by M0 composition GM, okay, where translation by M0 is the map that takes V to V plus M0, okay, is a translation of R2, okay. And this GM is A is an oriented linear isometry, okay, that is its matrix is in SO2. SO2. So it will be so if it's a linear isometry, its matrix will belong to the orthogonal group, okay, and if it is oriented, it will belong to the special orthogonal group. That means it will have determinant 1. And the fact is that such an oriented linear isometry will necessarily be only a rotation, okay, and in fact GM will be rotation by a fixed angle. Of course, rotation about the origin. Okay, so this is something that we need to see, and it's easy to see using some linear algebra. Okay, and the property of oriented linear isometries, right? So, so I will stop here.